Good morning, welcome back. We're going to be looking at the graph data structure today so we can actually look at one of the more complex data structures we are studying in the CS2420 class. As you can see right here, we have our graph data structure, our UML diagram for the class that we're going to be building for that. Taking a look at how we're setting this up, we have in our data member section, we have some data members we're going to use to look at the actual structure. We have a constant maximum. Now this is something we're going to use to say how big our data structure is going to be, because our graph data structure we're going to be using is a non-dynamic data structure, because again we're looking more at the connections within the data structure versus simply just the actual data attached to it. We also then have a Boolean array. It's a 2D array, using that to actually store the adjacency matrix so you can see which nodes are actually connected to each other or which vertices are connected to each other via edges. We also have our graph data, which is the actual storage of the facility that we're looking for that, the storage tool we're using for that. And again, it's just simply an array of type, because all we're going to be having within that is just a structure to hold all the different types that we're connecting with that and looking at to actually see the connections. And then we have our vertex count, which is the actual number of vertices that we have inside that, so we can actually see how big our graph itself is currently. Over in our methods section, we have some public methods. We're going to be looking at our constructor and destructor. We have graph operations methods for addVertex and addEdge and removeEdge. And we have some undirected methods so we can actually see how we're going to handle this if we're using an undirected graph. Because again, there are multiple types of graph. This lecture is going to be specifically dealing with undirected and directed graphs. So you could, of course, also add that directed and undirected with a weighted type. So you can have different weights to go up and down the graph itself. And we'll look at that another time. For our accessors, we have our two overloaded operators for left-hand and right-hand side operations of using the actual information within the graph itself, and also our size methods. We can check and see how big we have. We also have some methods we're going to use to check the connections inside that. And so we have our undirected connection, aka we're going to look and see if there's any connection whatsoever between that, as well as a directed connection using the rConnected method. And finally, the neighbors one, which will return all of the neighbors that belong to that specific node itself. For traversals, we have two traversals we're going to be looking at. We have our recursive traversal using the depthFirstTraversal, which is going to go as deep as it can and grab the nodes or the connections from that. And then our breadthFirstTraversal, which is our iterative traversal. We can actually go through and iteratively look over all those data structures. And let's go ahead and let's take a look at how that's going to be set up. So we have right here the actual class definitions section that's going to go along with that. As you can see at the beginning of that, we have three hashtag includes that go along with this actual class. Hashtag includes set, q, and assert.h. We'll be using those to actually go through and put together the structure we're building. Using namespace standard, because of the fact that we're using quite a few components out of the standard library, we have that using included along with that as well. And then because this is a templated type, a graph of type, we have that template class type line right there. Then we have our actual class definition sections. Let's go ahead and scroll down how we have that set up. Again, I'm using those little comments to actually denote the different sections of the class header file. We have our static constant maximum, and so we're defining this as a static int, and so we assign the value right here at this point. Now we're using 20 for this lecture and how we're setting it up. That could be arbitrarily any number we're looking at, but because we are using a non-dynamic structure, we're spelling out exactly how big our structure can be right here inside the actual data member section. We have our two arrays that belong to the data structure, the 2D array of Booleans, which is the adjacency matrix. We're going to use that to show the connections between the two different spots within our, between any two arbitrary locations inside the graph. And the actual graph data itself is stored in just an array of that type. And so we're already pre-assigning those values to be of maximum, so that we're using that keyword right there, or not keyword, I should say. We're using that predefined value, in this case 20, so we have that automatically attached to that right there as we actually define the class itself. We have our vertex count, which is the data member that's going to say how many things we're actually dealing with right now. And then finally, we have our private section. We have a recursive helper method, so we can actually go through and do the recursive calls we need. And that takes a reference to a graph, a vertex, and an array of Booleans. Looking over our public section, we have all of our methods we're going to be using to actually go through in that. And we have, of course, our constructor and destructor. Those, of course, take no parameters. We're simply going to default initialize those values and go from there. We then have our graph operations methods. These are the methods that actually go through and do stuff to the graph. And so in the graph operations, we have our addVertex, addEdge, removeEdge, and then our two undirected methods. So we can, just so we can show the logic that goes into actually doing an undirected graph as well, we have our addEdge undirected and our removeEdge undirected. So that would take care of it for either of those two different data structure types. In our Accessor section, notice that we have some very similar headers right here. We have type ampersand operator for the reference operator, which is our left-hand side operator, and then we have a type operator, which is of type const, because it's going to give a constant, aka our getter, or our right-hand side operator. And those frameworks right there. Our size, it's easy, no big deal. We'll take a look at that later. On our checking the connections, we have three sections right there, or three methods in that section, excuse me. And in those three methods in this section, we have an undirected connection. Again, looking at how can we handle this if we're using an undirected graph, aka is there any connection between those two positions? And finally, if we're using a directed graph, the more standard style, do we have a connection at all? And that's the source and target, and again, that's a const method. And finally, we have the neighbors method. And the neighbors method we're going to be using, that headers will say, who do we talk to? Who are neighbors of this specific vertex? And then in our traversals, again, we have those two different traversals, depth first and breadth first. Notice that the parameter structure for both of them to start off is the same, it's just the implementation that goes inside that is different. We're going to take a look at the constructor and destructor sections of our code. Again, when we're looking at our constructor or destructor, because up here at the very top of our file in our declaration section, notice that we are declaring a lovely predefined 2D array of adjacency matrix and a single dimension array for graph data. Because we have them already predefined as a private data member with the initialized values already installed for that, we're not using a pointer reference to it. We're simply just giving it, hey, I'm allocating immediately at the construction of my data member. I'm initially initializing this 2D array this big and my single D array that's the same height as well. And so because we're using that same maximum thing right there at at the declaration of our class, our constructor and destructor are going to be a little bit different than normal. So let's go back down and take a look at that. Looking at our constructor, we're explicitly only initializing our vertex count at 0. Now, yes, I know that ints automatically default to 0, but we're going to initialize this just because we have that nice practice of having our constructor have its regular job of initializing data members. And then notice that inside our destructor that I have commented out the delete array keyword and then the adjacency matrix and graph data. And the reason that those are both commented out is because since we are using a non-dynamic structure, we have that predefined array and predefined 2D array of information. There is no dynamic allocation of memory attached to this because as soon as I make my object, I'm immediately allocating all memory necessary to hold that object right there at the construction point. And so that non-resizable, simple array right there of information and simple 2D array of information is already right there. And so because of the fact that it's already defined with the size and everything attached to that, the delete keyword and with the array modifier on that, that's not going to do any good for it. It's actually going to cause a compile time error because it say I can't delete this when I leave the scope because it's already going to be handled immediately by the actual compiler itself. So the built-in deconstructor is going to handle all of this for us. So we actually have those commented out because we don't need to deallocate memory attached to it because it's going to handle immediately by the actual the C++ environment. We have that taken care of. But for purposes of actually looking to see what's happening in the destructor, we have to we delete the array of information for the adjacency matrix and the graph data. We simply have them as a little bit of no longer being used because the C++ compiler already handles that for us because we've already initialized that 2D structure right there at the beginning with the total value it needs. And if it wouldn't take that already, it'd be already handled by a memory allocation error. So we have that already totally taken care of, and so we're going to have that commented out and not worry about explicitly deleting that normally like we would inside our data structures. But again, when we're looking at the idea of when we're looking at the idea of the graph data structure, the data storage itself is not the point. It's the connections between the things. And so that's where we have to actually make sure we're looking at. We're not looking at storing the information, but rather the connections between the points we're looking at. First section. So our accessor sections are obviously our size and our two operator overloads. And so our size is just really easy. Just return vertex count. Now we'll be using the size method throughout a lot of the actual code itself just because it's a nice way to call and access that information. But it simply just returns that count of how many vertices we have right now in our graph. Really easy, no big deal, just a basic getter. Let's take a look though, however, at our two operator overloads. And so notice right here that between the two operator overloads, they're very similar. In fact, it's just the only difference is this lovely ampersand right here on the first one and the const keyword on the second one. And what this really is going to be is this is going to see how we're going to actually use the left-hand and right-hand operator, or left-hand side and right-hand side for using the square bracket operator. And so let's go ahead and add a comment to that right here. And what this is going to do is it's going to allow us to assign into the actual data structure. We're going to replace a value on what's at that location of the graph data. And so it's going to be because we're using that type ampersand, which is the type reference, which means we can actually overwrite what's at that location, replace it with a new type object, and replacing what's stored inside that location. So that's what we're doing right here. When we return graph data vertex, we're returning a reference to that, which means we can actually do a left-hand side assign into the square brackets like we would do with a normal array. The same thing happens here on the right-hand side operator for this, and that's going to be the const because it's simply a getter. And so the code itself, as you can see, we're simply just asserting that the vertex itself was within the range of acceptable values, and we simply then just return that value. The only difference is instead of returning a reference to it like we do on the left-hand side, we have a constant type, which means we're not going to change it. It's simply just going to get that value. And that's all we have to do the overloading of the operator for the square bracket operators, aka so we can assign into and or retrieve from the actual data structure we're actually using to store the data, the type stuff that's being stored inside this graph. And again, though, when we're looking at the actual graph itself, remember that the graph is more about the connections between the data rather than the actual data that's stored inside that. And so that's why we're going to simply just use this right here. If we wanted to go ahead and overload the square bracket operators for a list or an array, we could implement that same information right here, so we could actually go through and have a left-hand side operator or right-hand side operator, so we could change what's stored inside the array using that same approach right here. And this parameter itVertex, because the way it's set up is simply just the number that would be normally passed inside the square brackets right there when we're actually writing that in code. And we'll see that again in a later lecture. Once we move past the Accessor section, we have our operations section. Let's go ahead and take a look at the addVertex first. And so in addVertex right here, as you can see, it's a void type. It's going to simply just affect the state of the graph. And first, of course, we want to assert that the size itself is less than maximum. Again, we're using that size method call. I could also use the vertex count parameter right there, but I'm using the size to show that we're actually looking at that information, checking to see what's inside that, and also because of the fact that I'm changing vertex count at this point right here, it's a nice little way to say what I'm actually looking at for that. And then a new vertex number, so that vertex count, because it's going to go up by 1, because we have that off by 1, so 0 has 1 would be the second one in there. That's why we're able to do that right there, where the vertex count gets that new vertex number, so we can actually put them in and have that go through. And then my vertex count, my private data member, is going to go up by 1, because once I have that point, once I've added a vertex, I'm going up in size in what's actually inside there. Then we're going to look at our for loop. This for loop is going to go through and actually go through the actual data structure. And so we'll start off at 0, go through, make sure that other vertex number is less than vertex count, that lovely thing we just plussed right here, the number of vertices we have inside the structure, and go up by 1 each time, no big deal. And then I'm using these two lines right here, adjacency matrix sub other vertex number, new vertex number, and adjacency matrix sub new to vertex number, other vertex number, aka both positions on the 2D array. And we're going to go through every position of 0, 1, and 1, 0, those matching spots that go through that, up to 1, 1, because we want to make sure we have all the appropriate values for that. And we're going to assign them all to false. And what that's going to do is it's going to go through and initialize all the current connections between the node we just added and every node previous, initialize them to false. Because again, when you default construct a 2D array or any data structure inside C++, the initial values that go inside that are undetermined. And by doing this, we're explicitly assigning those values to be false, because when we add something to our graph, we have to explicitly say that the connections between it are all false when we first put it together. Finally, the last step of adding a vertex is we want to go through and set at graph data. We want to do that new vertex number, that number we just put in, which is just went up by 1 because of the total count. Again, that making it so it'll fit right within that. We're going to say new vertex number is equal to value. So we attach the value that we just passed as a parameter and assign it to that spot that we just put in there. And again, we're using that addVertex so we can actually put things inside the graph itself. The next operation in the graph we're going to look at is the remove edge. And as you can see in the remove edge method, we take a source and a target, looking at the connections between those points. And this is a directed method. And because of the, first we're going to check to make sure that the size itself is within the boundaries as well as the target within the boundaries. We can't make sure that's going on any spot that doesn't work. The next thing we check is to make sure the adjacency matrix from source to target, making sure the connection from this spot to that spot, we're going to assign that value to be false, because we're saying there is no longer a connection between those two locations. The addEdge is the exact inverse of that. Again, we have to check to make sure that the size and target are both of them, that the source and the target are both of the less than size, because we have to make sure it's actually a valid number. And then instead of setting it to false, we simply set the connection between source and target. We draw a line between them. Oh, there's now a connection. We assign that to be true. If we take a look at the undirected version, because undirected doesn't care about what direction we're looking, the same thing works in the idea, but for remove edge, we're going to take both directions out. So we're going to set adjacency matrix sub source sub target is equal to false, as well as adjacency matrix sub target sub source, making sure both directions are set to be false, because when we're taking that undirected, both connections actually be maintained. And so we have the same inverse on that for addEdge undirected. And so we'll set from source to target to be true, as well as from target to source to be true. Because if we're dealing with an undirected graph, it doesn't matter which way we're going, there's a connection on there. And so adding an edge or removing an edge is simply as easy as assigning a Boolean value to the connection we're looking at. And if we're dealing with an undirected graph, that both of those directions get a Boolean true set to it, or a Boolean false if we're removing that edge. Not a lot of work to actually do the operations for that. And then if we have a directed connection, we're going to check to see if the directed connections on there will assert that, of course, the source and target are valid values. We check to have Boolean isn't_edge is set to be false because we assume it's not there first. And then we'll assign isn't_edge to be either the source to target or target to source. If either of those are true, it goes into true, and we have the short circuit evaluation that can potentially happen. Or if both of them are false, hey, it gets false as well, no big deal. And simply return that value. As you can see then for our directed location, the are connected, it's even simpler. It's simply just, is that connection from source to target existing? And so if it's undirected, we don't care about which direction we're going. If it is a directed, it's merely from source to target. And so that source and target, those are the number of the vertices that we're actually looking at. It's very important we put them in the right order when we're actually looking at how we're gonna make that connection, because especially on a directed graph, the order of the parameters do matter. So those are the operations of actually taking a look at the connections. The next one we have is looking at our neighbors. This is gonna be really helpful for doing a bunch of other connections. This is how we actually look at the graph itself and see who's belonging to us. And this one's going to return a set. And again, remember, when we're talking about a set, it's the lovely mathematic concept where it's discrete, all unique values, and the is no order to the actual set. So it's simply just a collection of values without order. And so because of the fact that it's unique, discrete, and has a lack of order, we can't use a regular for loop to go through that. We'll have to make sure we use an iterator. And we'll talk about that when we actually use this method in just a minute. So again, we have to assert that size is valid, or that vertex is valid, aka it's less than size. We then create an array of ints, we then create a set of ints, not an array, because we have to actually make sure that they are unique and they are discrete values. And then we're going to iterate using a regular for loop. We're going to go from 0 up to size, going up by 1 each time. And we're going to check to see if the adjacency matrix, aka that 2D array of Booleans at that location, again, this is a directed location. If the adjacency matrix from vertex to index matches, then we'll add it in. If there is no connection, we don't add it in. And simply then at that point, we go through and return that vertex of neighbors. And so this makes sure, because we're using a set type right here, that standard set, the standard library, we won't have any duplicates. So if there was a connection that already existed in there, that index wouldn't have to be worried about adding in more than once. So we've got that making sure we have only a discrete set of values that gets added to that. And return neighbors, easy peasy, we're good to go. So once we've got now those last of those connections and neighbor ones, our next section we have are the traversals. So let's go ahead and take a look at first the depthFirstTraversal public method. In our depthFirstTraversal public method, as you can see, the first thing we're going to do is define a Boolean array of visited vertices and then set that to value of maximum. Again, we're using that maximum constant we've decided at the beginning of the class. We're going to use that throughout the entire structure. And we want to have that Boolean variable, or that Boolean array, available to see if we've gone to that spot yet. Then we're going to use the assert command, making sure that we're within range, because of course we want to make sure that vertex is a valid number. It should, but just in case. Assert's a fantastic tool. We're then going to use the standard library's fill_n command, aka the method that allows us to put a set of default values into a data structure one at a time. So we're using visited vertices, that lovely Boolean array we just created. And because we can't assume that we can't assert what values are in, we're going to go through up to size, grab the size of that current graph that we're passing as a parameter to this, and we're going to assign the values of that all to be false. So we're going to go through and boom, 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 put them all as false, making sure no matter what, we haven't gone to any of them yet. And then we're going to call our recursive traversal helper method, which is depthFirstTraversal, passing it the graph, the vertex, and that new array we just made, visited vertices. So that goes us to our lovely little helper method right here. So let's go ahead and expand that out and scroll down so we can see it really well. And so in a recursive helper method right here, as you can see, we have it's a void type again, because we're using the idea of just traversing and going over and seeing what's inside the graph. And as part of recursive traversal, the first thing we have to do is we have to declare a set of type int. It's our connections, and those are the neighbors that belong to that current vertex. Who does this one talk to? And again, notice that we are not using type inside this. This is that connections of ints, and each connection we have is an int. It's just a number of the vertex we're dealing with, from 0 up to maximum -1. We then have a iterator, a way of traversing that set, and that's a set iterator. We're using just the standard library set iterator we're going to create for that, so we can actually go through and look at that data structure. Once we do that, we're going to set visited subvertex to be true, because we're at that vertex. We're right there. We visited. We've got to that point. So as soon as we first get there, we're starting off that individual one we just called from that vertex parameter. That's where we stepped into it. We pass it right back in here, and we set that array position to be true. We output that variable, because we're using that traversal saying what we've gone through, and we've gone through and actually exported it out. And then we're going to use an iterator to loop over that structure and check to see what's going to happen. So we're going to use the iterator. We're going to start the iterator off at connections.begin. So connections is the name of that lovely set, and we're going to go to the beginning of it. So iterators are that fantastic tool. We can actually just get right in there and go to the beginning of it. And then we're going to go through and we're going to iterate over the structure until we're not at the end anymore. Hey, we don't know how many there are. It's a set. We know we don't have a sub index we can simply just go through and get to, sub 0, sub 1, sub 2, sub 3, whatever. We have to actually go through from next to next, next. And so we're going to use the iterator, that built-in structure, to go from one to the other. And because the iterator has been defined for us, all we have to do to increase the iterator to go up is just do set iterator plus plus. So we already have that plus plus operator we can use to simply just go from the next one to the next one to the next one. But because we don't know how big they are, we're going to use that not equal to connections.end so it tells us when to get out of that structure. Then we're going to, inside that, we're going to check to see if we visited the dereference value. So set iterator is that lovely iterator that looks inside that connections set. And so we're going to dereference what's at that iterator, aka the value of that spot at the set. And if we visited that, we don't have to do anything. But if we haven't visited that spot, then we're going to call that recursive helper method again, passing that dereference value of that new index. Hey, there's that vertex right there, that spot we haven't gone to yet. And so that means we're going to recursively come back and go into that new call, come back in here, rebuild a new set of neighbors, a new set, go through, make an iterator, go through that, and then assign that spot to be true because that's what we checked right here. Oh, hey, there's that reference, bingo. We assign that spot to be true, which means we won't come back and check it again because we've already visited that location. We'll then go through, print it out, and then grab that and go through and iterate through that structure, that set's connections. And if we visited a spot, we'll go through and recursively do it. And again, we'll break out, come back and get that spot, and go back in and recursively go through. And that's where that depthFirstTraversal, we're going to go as deep as we can, keep on going deeper until we get to the spot where you start breaking out of the recursive call and print those out. And that's where we go for that. So as you can see, the recursive call allows us to go in and use the idea of a set as well as a set iterator to traverse all the neighbors of that. It's that neighbors method that we had that tells us who do we have as a neighbor to this location. We can actually see that. We'll actually see that when we do the test method here in just a bit. Finally, we have our non-recursive method, our iterative traversal. And so as you can see, our iterative traversal is pretty big. And just like we saw in the iterative traversal of the tree data structure, when we're doing an iterative traversal of a graph or other non-linear data structures, since we don't have the stat call on the actual calls that are going through the actual operations, we have to actually build another data structure to keep track of where we're at on top of that. And so as you can see right here, we have a bunch of data numbers that get defined just for this method, or local variables, I should say. And so first we're going to assert, of course, that it's in the right area. We then, again, make that visited location. We're going to also still keep up with connections and an iterator go over that as well. But then we're also going to implement this lovely queue right here, and a queue of ints for vertex queue, because we have to keep track of which queue we're dealing with right now. Because otherwise, the recursive call handled all that information for us as part of the call. Part of the call goes in, goes out, goes in, goes out of the recursion. This one, because we are not using recursion, we have to keep track of that. And we're going to use the queue to actually do that. We're then going to use the fill end command again. We're going to go through and fill that lovely visited array, again, all with false, just like normal. And again, just like in the recursive thing, we're going to assign that specific index when we're starting off with. We've been there, so let's mark that to be true. Then after we've done that, we're going to output that value. Again, very similar to what we saw inside the recursive solution, but here's where it gets different. We're going to say, we're going to push onto the queue that current vertex. And because it's a queue, we can go through and get that value and put it right on there. And so we're using the queue as the first in, first out is what we have. So we're going to put that onto the queue, and we'll hold that in the queue as long as we need to. And so that queue can actually get growing pretty big. Right now there's only one thing on the queue because we just started off with it. And then as long as that queue is not empty, we're going to go through and we're going to say connections is equal to current graph.neighbor. So we're going to grab the first neighbor set from the first thing that's on there. We're going to store that as a connections, that lovely set we have right here. And then we're going to take the first thing on the queue, we're going to pop it off, we're going to get rid of it. And right now that's the first one, which means that our queue is empty. So right now, if nothing's happening, that queue is empty and we're done. We're then going to use that lovely iterator, same loop we did just a minute ago. We're going to start the iterator at the beginning, not at the end, and go up by one each time. But then this is where it's different from the recursive solution. If we haven't visited that spot, then I'm going to take that spot, dereference it again, and set it to be true, because now I haven't visited. I have visited, so I have to assign it to be true. I'm going to output that value that's in there, dereference it, just like we had earlier. But then I have the vertex queue.push. I'm going to add that to the queue, which means I can add multiple things to the queue in this loop right here. So this loop will have a nested sequence of calls. So it's going to build and build and build. And each time I go through, I'm going to add in the neighbors into that connections, which means I could go through and add all those back into the queue at that point. And I can see a different set of traversals. And so the code that we have on a breadthFirstTraversal versus a recursive traversal of using a depthFirstTraversal is a different way of actually looking at that. And so we're going to see how we can actually do that on our next lecture. We're going to see these traversals in action and see what actually happens with that. So thank you very much and have a great day.